So once again, thank you everyone for attending, and thanks again to Lockheed Martin for sponsoring our seminar series. Today's speaker is Dezhen Song, who is a professor and associate department head for academics with the Department of Computer Science and Engineering at Texas A&M. He received his PhD from UC Berkeley, his master's and bachelor's from Dezhen University. His primary research area is robot perception, network robots, visual navigation, automation, and stochastic modeling. He received his an NSF Faculty Early Career Award in 2007. He was an associate editor of IEEE Transactions on Robotics, an associate editor for IEEE Transactions on Automation, Science, and Engineering, and senior editor for IEEE Robotics and Automation Letters. He's also a multimedia editor and chapter author for Springer Handbooks of Robotics. His research has resulted in 1 monograph and more than 110 refereed conference and journal publications. I'm going to let him introduce his topic that he's going to be talking about today. Welcome, and carry on.
Well, thank you, Professor Yu, for the introduction. It's a great pleasure to come here to actually virtually to give the talk. Today's talk is actually entitled Robust Perception. In fact, it's I would say it's a long journey instead of a single paper presentations. It's the result of many years with collaboration with my students and my collaborators. Also, thanks for the funding agency who supports that. So the topic we're going to focus on the role of sensor fusion in the robot perception. But we're going to start with the 3 questions that we're trying to answer. What is sensor fusion? Why we need it? How do we perform it? So we have to put this in the context of robotics, because this is our main area. So if you're familiar with robotics, you might heard about this thing called SPA model. The robot taking information from the environment as sense, and they form the understanding of the environment as self, the plan for next action, that's a plan. And then it execute the commands and cause change of status. That's the actuation or action. So SPA model, you can see the information flow in from the sense side. So if you have poor perception of something, then the rest of the chain will break down and garbage in, garbage out. So, and that is the reason in my research, I focus on the sensing perspective. So of course, the sensor fusion definitely falls in this category. So I want to put this in the autonomous driving context. This is actually one of my application area of my research. So you can see that modern autonomous vehicle have many sensors on board, from long-range radar to lidar, camera, short distance radar, and ultrasonic, and also GPS, inertial sensors. Those it's a suite of sensors being installed. But what I want to mention one point is that is using many sensors does not equal to sensor fusion, because sensor fusion itself is trying to reason the robot status using many sensors. So we can just put this into a block diagram like this. So it's still built on the SPA model, you can see, but we kind of amplify the sensor part. So different sensors have different data streams comes in, you process them individually, then you try to fuse them, get a better understanding. So we like to put this in a mathematical context. That is, each sensor will provide an estimation of the state, which characterizes the status of the robot and the environment it lives in. And we can use a vector to represent, that's the X. This has a little bit of hack because it's the estimation of the state. You will also come with some sort of uncertainty assessment of your estimation, how good it is. If you, in many contexts, it will manifest itself as a covariance matrix of the random vector X. So you might have different representations, but this is just one common way of characterizing uncertainty. So in the sensor fusion process, we like to aggregate these estimations to come up with a more reliable, but potentially more accurate estimation of the states, and also update its uncertainty range. And that you can put this in, this gives you a mathematical context of sensor fusion. But we also need to understand what are the states and what characteristic of uncertainty they have. So then sensor fusion itself is trying to reduce the uncertainty. That's two very important metrics when it comes to sensor fusion, robustness and precision. These two things are kind of gonna be the main themes in this talk, how to especially emphasize and improve upon those two metrics when you perform system design or algorithm design in the perception tasks. So to understand this, we have to get a clear idea of where uncertainty comes from in estimation and how does it look like. I will use a common characterization in the localization and mapping tasks. So in this particular case, I call it bounded uncertainty. So a robot is a 2D robot moving in a very simple trajectory, and it estimates its positions periodically. You can see it's a little black dot. That's where it estimates position. So the state, in this case, is a 2-dimensional vector, x, y. And it also has a uncertainty range. It's actually in this ellipsoid, shaded ellipsoid region you see. As you can see, the uncertainty grows over time because essentially it's a summation of the random vectors over time, uncertainty range will grow. And this is called a bounded uncertainty. It has a continuous, close to continuous process of uncertainty representation. If everything would look like that, problem may be easy to solve because in reality is a lot of times things break down. So I call this unbounded uncertainty. For example, your robot ran into a corner with no landmarks to help you estimate your position. Your localization mechanism fails. That means your uncertainty becomes unbounded. It's not a nice little ellipsoid circle to help you. So this is the issue that cause a lot of robots to essentially fail its task. This is the robustness issue. And you can say, in this case, you can still say it has uncertainty, but this uncertainty maybe is ill-conditioned or cannot be estimated due to the failed computation or environment-introduced constraints. This is very common when you design perception system for mobile robots. For example, a camera, if it faces a wider wall in a pure white environment, you have no idea to figure out its location because it's low landmarks. Or if you design you have a simple sensor like IMU, certainly you have a strong vibration caused by environment, cause you out of range, then you will have a catastrophic reading. Also, even the simple wheel encoder might have the issues of wheel slip. Suddenly, your robot ran into sand and the wheel slip like crazy, and your sensor model, your estimation of positions are way off. So those things happens. In fact, if you are system engineer, you do a lot of field work, you're gonna feel like most of the time we get stuck to deal with those special cases. So mathematically, this is a more important problem than precision problem or the existing problem we are working with. So what is the sensor fusion from mathematical perspective with this context of uncertainty? We can really look at this from 3 different layers, or simplest one, or the most fundamental one we have to work on, we call the feasibility. Given the estimation from each sensor modality and its uncertainty, can you figure out aggregate states? You can hook up the straightforward way could be a switching, right? You just pick up any sensor, or maybe you can do averaging, or maybe you can do some smart optimization. But that is the feasibility. Can you get this result out? But more importantly, if you go to next layer, that would be precision. If you by taking uncertainty into consideration. So what is your new uncertainty? How do you minimize it? In physical covariance metrics, it's going to be manifest itself into like maximum likelihood estimation, some sort of least square problems you can solve. You might immediately realize that these 2 layers can only deal with the situation that uncertainty is bounded in a nice closed form format like we had in the previous example. So then that goes to the most difficult one and the ones that we often run into. And sometimes we don't even know how to write it mathematically. We try to give it a mathematical characterization here, which might not be accurate, but we have something to start with, so-called robustness. So you're given the uncertainty measure and the readings estimations of the states, trying to ensure your output uncertainty is bounded. As long as you have some input, uncertainty is bounded. Is this possible or not? Can you solve this? And this is more of the robustness issue I deal with. There's not just the problem of existing approach. Most of this work is assuming everything is bounded, then you solve that the problem. You don't know you're running into a robustness issue. Like if you run a continuous simultaneous localization problems, and especially VSLAMs, if you are familiar with the impact, you're gonna see that sooner or later you have your computation gonna break down because you are not aware of this issue in the computation, and you're not aware by design in particular. So this is the kind of problems that we have to address. The robustness is the key thing here in perception. So how we get there, here in this, I'm trying to using the previous examples. I mean, how personally I got into this research area and trying to understand, in this problem through different robots and perception system designs. So I'm going to start with two early projects we did in our lab. And the first one I'm going to talk about is the autonomous motorcycle we built back to 16 years ago when I was a grad student at UC Berkeley. The design was trying at the time where we are participating with DARPA Grand Challenge. 2004 and 2005 we did participate 2 times. If you knew a little background, you're probably aware that DARPA Grand Challenge essentially get this wave of autonomous driving trend started. As an early participating team, the DARPA gave out trying to use a $1 million prize to encourage people to come up with autonomous driving strategies. This is over 16 years ago. At the time, computation and sensing are very primitive. Also, the environment they're dealing with is not much easier. So DARPA is trying to kind of doing this cross-sourcing type of approach to figure out who can do this. So the competition is to design autonomous vehicle that can drive over 100 miles on a desert terrain, because the real motivation behind this is there's the US was in war with Iraq at the time, the second Iraqi war. The convoy trucks can get attacked by roadside bombs. And they're trying to see if they can get some autonomous vehicle deliver the goods to the frontline soldiers. So that's the background story behind it. So that's why the Nevada desert we choose as the competition track. And as a group of grad students at the time, actually no faculty involvement, we decided to go with one of the most challenging platform as motorcycle. The perception system in this particular platform is really the simplest that we can afford, and also the platform can afford, because this is severely power and volume constrained platform. You cannot put a rack server on top of this platform, and you don't even have enough width to have a wide baseline camera system. So we have this minimum perception design with GPS, IMU, and camera that got us into the sensor fusion domain. The idea is, of course, at the time was basically most of the things we do is we call the GPS waypoint navigation with camera to help to navigate the terrain. So GPS itself is not accurate enough at the time. We don't have RTK GPS back to 16 years ago. It had only accuracy around 10 meters, sometimes even worse. GPS itself will not be able to keep the vehicle on the road. We have to recognize the terrain and guide the vehicle in the local coordinate system while following the global GPS router at the time. So we solved we also have to use the sensor to help balancing the vehicle and putting all these navigation tasks together. I would realize a lot of tasks you do. You just have to combine those sensor readings all together. This is basically, as I'm gonna go into detail later, is no single sensor can solve the problem that we are facing. I'm not going to run the entire video. I just want to give you the idea of the background behind this. Now I want to move into next slide. During the competition, actually, this is actually a little bit of history behind it. One of the team's name is Velodyne. If you're in the autonomous driving domain, you might be very familiar with this name now. Because essentially, Velodyne starts as a DARPA Grand Challenge 2004-2005 competition team. Their biggest contribution is to prototype the 3D lidar system. This is the one of the early lidars that built, and this eventually become the Velodyne product that we are very familiar with in the autonomous driving domain. This is your witness history here. Took you back to 2005 when this whole thing has a size of a couple of feet in diameter. Right now it's much smaller. So after the DARPA Grand Challenge, you all know that we have this thing called DARPA Urban Challenge. We did not participate in that because one of the explicit requirement for that competition is 4 wheels. We only have 2. So we did. On the other hand, I moved to A&M to be a faculty, but my team at the rest of the team at the UC Berkeley formed a company led by Anthony Lewandowski called the Berkeley 510 system. That team is acquired by Google. The task of that time is to build 2 vehicles you all know today. One is Google Street View vehicle, the other is Waymo, it's an autonomous driving vehicle, as you're all familiar with this today. So, I mean, we are very happy that our team play an important role in this piece of history back to the days. But if you look at the Waymo vehicle, you can see the Velodyne lidar on top and the other suite of sensors being put in together. It's gradually already formulate kind of like a standard template of how many sensors you have to use for autonomous driving. But actually, sensor fusion is not just for autonomous driving. It's also important for service robot. In this case, I'm going to talk about a very expensive service robot. That is Robonaut, the robot astronaut that being installed in the International Space Station. So in this particular example, I'm going to show that the importance of precision and robustness that definitely will be needed in such a system design. So the robot astronaut itself is a humanoid, actually not exactly humanoid. Up body is a humanoid. The lower body is a little different. But it is also the only robot that wears clothes. If I were my first thought maybe just make the robot looks better. No, it is actually for its purpose. The clothes protects the sharp edges of the metal surface. So when this robot work closely outside the International Space Station, they will not cut the astronauts spacesuit open. It will not cause problem like that. So it's kind of protection mechanism. It's a soft armor. But it also tells you that the robot has to work in a very tight space. And you need to know its precise location while it's moving around in the space. There's no GPS. And the robot also need to know the 6 degrees of freedom pose. And so you need to solve that standard localization and mapping problem we're talking about. This is in robotics called the SLAM, simultaneous localization and mapping. The purpose to find solutions for 2 problems at the same time. So localization, where am I, especially in this case, the 6 degrees of freedom pose, and the mapping. What does the world look like? And this really has a lot to do with the sensor type and then your landmark type and things like that. But you have to characterize your environment as a map. All right, so how we deal with this? The robot, you keep in mind, when it was first designed, it was designed as a teleoperated robot. It's not designed as a autonomous robot. So it has a whole bunch of issues with this perception system we have to fix. But what's important to this, to keep in mind, is working environment. It could be inside the International Space Station or outside. So it is, if we design, we cannot add any additional sensors to it. We have to use onboard sensors. So in this case, what's available to us we identify will be most useful is binocular vision that being installed in its head, and also IMU being installed, the high precision IMU installed in its body. But it actually gonna sustain some sort of vibration from time to time. So IMU may get off, and also vision may get challenged when you face the dark side of the universe. So you might not have a good landmarks to help. So basically, it's very important you come up with a robust solution that can deal with this environment change when your camera can be challenged, the dynamic range can be challenged, and also your IMU can be challenged. The problem is that when it was designed, there's no synchronization among those sensors. So that's another problem we run into. We have to figure out a software solution to this. We build a hardware simulation system. So we have a binocular vision system with IMU processing board, but does not provide sufficient synchronization by hardware, trying to see if we can achieve a good result. Eventually, we work out that problem. In fact, one of the results, if you're familiar with the Visual SLAM, this video, it might look very familiar to you. As a little pyramid, essentially is the perspective of the camera we estimated. The dots, the red and the black ones are the landmarks, it's feature points being extracted and correctly matched to each other. Then in this particular example, the robot is doing a space A-shaped dancing. We're trying to give people the idea that this is able to do a full 60-degree of freedom estimation. This, of course, it doesn't tell you how the integration of other sensors works, but essentially it is a result of all of this working together. The idea of combined inertial sensor, essentially it is what we call a proprioceptive sensor with a camera, which is a exteroceptive sensor together. Is not a new concept. It is a common way that the robotics do to combine the different property sensors, different sensor properties to achieve a robust result. In fact, it is also used in, I'm gonna stop this video and move to next slide. Okay, it's all being used in some handheld devices, like in iPhone. Right, so in 2017, at the release of iOS 11, the Apple CEO Tim Cook at the time announced the very important milestone of augmented reality. This is the release of ARKit. This is the first time a regular user outside the lab can really experience what augmented reality is, and that thing can run on its mobile platform with limited computation resource like a simple phone. And this is a very important milestone, and also is very important for people in the robotic perception domain, because essentially what it's doing, the phone is doing is a visual inertial SLAM algorithm inside the iPhone. They combine the IMU on board the Apple device, and of course its cameras on board, computing in real time compute the camera pose, essentially the phone pose, in relation to the objects in the environment. And then that allows you to insert our virtual object inside it. So this is kind of started this era of augmented reality for mobile device for mass market. It's 800 million device has it, 800 million people can experience it. This is really probably the most accessible robotics SLAM software we ever seen. And during the development, the one typical problem Apple developer have to address is, in Apple's headquarters, there's, if you happen to visit there, you can see that there's a lot of white walls. If you walk in the corridor, you can have an environment of pure white walls. That means if you do visual SLAM, you have no way you can compute your camera positions using passive vision, or even depth sensor if you have one, because this is a monotonic environment, no feature to register. So they have to use the IMU to integrate that using this very efficient computation framework they developed. Of course, as a result, you see a very good augmented reality development. You might ask me why I know this, because my PhD student developed the ARKit in the iOS 11. He's the primary developer, and I'm pretty happy that he's making a big impact in the augmented reality area. So another reason is why, for sensor fusion. Now we get into a question of why. The autonomous driving, you just have to do it. So this is a failed example of sensor fusion. I want to show to you. It happened not just once and multiple times. Tesla vehicle collided with other vehicles on the road. If you pay attention to this, you might see that this is a cargo van that just flipped on the ground. It is purely white. And what the Tesla vehicle relies on mostly is a vision-based approach. You might say this is actually very, very strong signal that can be picked up by radar sensors that is also on board on the Tesla. Why you do not do a good job combine this? Yeah, that's a good question, because they don't do sensor fusion well enough. In fact, this is not the first time it happened. So you can see, if you go back to the autonomous driving applications, sensor fusion is a must, because in reality, there's no ideal sensor for autonomous driving, or even for any mobile robot living in a real environment. If you look at the 3 primary sensors we're using, camera, lidar, radar systems, you can see, camera has problem of the weather, camera have problem lighting conditions, and the radar does not have good spatial resolution, and the lidar does not deal with weather well enough, also have the cost issues, things like that. If you put it into different tasks, from very important tasks from object detection to localization to adaptivity to different weathers, you can say none of these sensors can deal with all these things well. So you have to combine these together. Of course, different sensors work on the different signal spectrum to give this own unique perception range and unique perception capabilities. If you use that well, you can increase the safety, and more importantly, ensure that the vehicle will be able to avoid things ahead of time. So one thing I want to really point out is the sensors, although there are many types of them, you can quickly classify them into the 2 categories. Extroceptive sensor, camera, lidar, radar, acoustic, even including the GPS. They rely on external signals. Anything rely on external signals may have trouble when the environment is become extreme, like a poor weather conditions, snowstorm, whiteout, the severe thunderstorm time. You might have interruption of signals. You might not get what you want. Another group of sensor is a proprioceptive sensor, inertial sensor, encoders, force sensors. Those sensors, the perception process is less affected by the external environment. They're mostly reliable in the working sense, but they're not very precise. They do drift a lot. But you can see that biologically, humans we actually also have these 2 types. We combine them naturally, just like when you close your eyes, walk for a few steps, you have no problem of avoiding the obstacle in your memory. You have a natural integration between these 2 sensors. So the 2 classes of sensors. So when we design these things, we have to take them into consideration. If we look at this from the uncertainty perspective, you can see extroceptive sensors uncertainty model would like a bimodal distribution. If it works nicely, it's relatively accurate. Its amount of drift is small. But if it doesn't work well, you have a really big uncertainty range. Could it be as big as the environment itself? That's the thing. But proprioceptive sensor, it has a growing drifting uncertainty range grows as time goes, but it rarely breaks down completely. So it actually have 2 different kinds of uncertainty properties. That's actually determine why you need to work with them both to make a reliable perception systems. So then we can go deeper, dive deeper into sensor fusion problems. You can see we have to solve a bunch of the small problems to make it happen. So we have to make sure we synchronize all the data readings from different sensors. So temporarily, we know they receive data at the same time, and we need to make sure they're working at same coordinate system so we can combine it together. So calibration is a must. Also, there's correspondence issue. If you do not have good synchronization and calibration, for example, your data may capture by different platform at different time. There's no way to synchronize them. Then you have to figure out how the objects of interest are corresponding to each other in different data streams. That's become a correspondence issue. Of course, if you solve those problems, then you have to face the problem of putting them together to come up with the combined aggregate state estimate and its associated range. It will be the fusion. You can do simple rule-based filtering and switching. You can do filtering-based. You can do optimization-based approach. And it's up to you to design these things. Of course, at the end of the day, you could have designed a new sensor that leverage different modalities simultaneously, which we will touch at the end of this talk. So if you also can look at this from the three layer of problem we talked about and earlier, you can see, if you talk about feasibility of the sensor fusion, that just covered, the first bunch of this category sub-problems. And if you go down to a little bit deeper for precision, then you really need to look into optimization filtering-based approach because those give you explicit closed form representation of uncertainty. Maybe you're doing the error propagation model derivation, and you minimize this and become an optimization-based approach. Yes, you can do that with precision model. But of course, robustness, if you want to improve that, you need to have cover all of them because you have a situation that you might not have your uncertainty range in a closed form approach. You should be aware of this ahead of time when you design system for robustness. And we're going to touch this in next few slides. But before we're going to start with the 4 examples. So this is just a quick review of the 3 layer of problem we're talking about in sensor fusion to put it into the context. So the 4 examples I'm going to talk about, I'm going to start with the feasibility, the calibration enabled sensor fusion. This is really just solving the first layer of the problem, feasibility side. So for when you're working with exotic sensors, in this particular case, is a ground penetration radar that I've been working on. Why we would want to work with it? Because there's need. The need is to keep our infrastructure well maintained. So we have US freeway system has been established a long time ago, of 75 years old in some segments. So bridge already at the end of their service lives. So they need frequent inspections. So the bridge collapse accident happens from time to time. But problem is there's no way we can afford a manual inspection. That's very lab intensive for all these bridges. So the deteriorating infrastructure call for a automatic inspection system for, especially robot mounted inspection system. In this regard, one of the most capable sensor of doing this is the ground penetration radar. So we have a ground penetration radar. We found that this radar system is actually a terrain following device. It does not have the ability to provide a full-scale mapping to provide the inspection result that can be used by repair crew with the precise localization. So we try to combine this with other sensors. Like camera and lidar, as we're all familiar with, because this is going to help us. But problem immediately pop up is, how can you make this sensor work together? Don't even have joint coverage range. It's ground penetration radar, by definition, is look at things for things underneath the surface. But the camera and lidar, they only look at the surface object. But you still need them to co-register in the same coordinate frames. If you link this, you want to make sure they can be expressed in the same coordinate system. It's essentially a eccentric calibration problem for a sensor suite. In fact, we can narrow this down because we have a lot of sensors in this design. We have cameras, we have GPR, we have lidar and encoders. In fact, we just need to solve, here we only focus on the calibration between camera and the GPR because the rest of them are solve the problem in the robotics domain. I don't have to explain them here. So to do this, you need to design a dedicated calibration rig. So what is the purpose of this? You want to create a joint coverage for both sensors, for both camera and the ground penetration radar. In this design, you can see, if you can see my cursor, we have a checkboard under the surface of an artificial bridge. On the checkboard, we have a metal ball we place on the corners of this checkboard pattern. And what that helps is this metal ball definitely will create a very strong essential signal in the ground penetration radar because it's a metal object. And it actually creates signal is a parabolic signal, and we can extract the coordinate from parabolic signal extraction. On the other hand, we set up a mirror mirror that allow the camera to look underneath the calibration bridge and to be able to see this checkable. Of course, we also have to estimate the mirror pose. So this consists a calibration system. They provide data for us, be able to estimate the rigid body transformation between the camera coordinate and the GPR coordinate. So the problem definition is just trying to take, using the camera images, those parabolic signal created by the ground penetrating radar, and to figure out the rigid body transformation. So the problem itself essentially is to estimate how we can be able to figure out these two types of sensor region can relate to each other in the same spatial coordinate system. So, I mean, I'm not going to the detailed design. I just need to give you the idea is, well, you need to be able to estimate the camera and the mirror pose. And also you have to be able to extract the signals from the ground penetration radar to get those metabolic center positions. When you get all this together, you can fit them into a MLE framework, maximum likelihood estimation. Also, you can have a nice closed form representation of your uncertainty range, because everything we do, we can kind of reasonably assuming Gaussian assumptions in pixel coordinate, also in the GPR coordinate, then we can derive how our uncertainty of the works in our estimate transformation. So essentially you have to really put it into perspective projection model, mirror reflection model. Of course, you estimate the camera pose and the mirror pose simultaneously in this, put it into together with the GPR, the parabolic extraction model, because each metal ball creates a parabolic response in the GPR reading, and the parabolic vertex essentially is where the ball is in the GPR coordinate that allows to obtain its positions in the Euclidean system. So putting all this together, minimize this, then we can do error analysis to obtain the uncertainty. That essentially give us the answer we want, the transcoordinate system transformation, and the kind of uncertainty we'll introduce to the system. Later on, when we do sensor fusion, these all play a role in putting this together. So, of course, we test it in our ground truth and with ground truth, and it works. I mean, you have to believe me on that. But the time does not allow me to go into the details or read all those arrows and maps and things like that. We also, of course, combine the visual SLAM algorithms with this to allow the we to register GPR reading in the visual SLAM Euclidean coordinate generated by visual SLAM, the map generates to register those reading together in the Euclidean system. And you can see this is two test locations. One is in our corridor. We can actually see the cable being deployed in beneath the floors, and we also really inspect a bridge on the right hand side. I can see the rebars and voice there in the GPR readings. More importantly, those readings being registered to the 3D coordinate system. We know precisely where they are. If you want to open up the bridge to break the concrete, we know where to operate to fix the bridge. So that's kind of that help us to serve that purpose. So next example I'm gonna go into is the more focused, is really more focused on the precision side, and also address the correspondence side of the sensor fusion problem. So what is this problem we're working on? We go back to SLAM problems that we introduced. The robot has to estimate its location at the map. In this case, we have two types of robots. One robot is relatively big and it's also expensive. It's equipped with lidar. The other robot is actually cheap home service robot, only have a camera. So the idea is, can we combine the map created by the expensive robot to provide that to the cheap robot, so the cheap robot can achieve similar level of robustness and accuracy that the expensive robot can do. So essentially, we try to do a map fusion, combine the monocular SLAM result with a lidar SLAM result. With the hope that this result is going to be better in accuracy and robustness. So of course, this map, once it's combined, it can be used by the cheap robot without lidar. So it is going to be make it more accessible to other robots in the environment. All right, so if you look at the case, some typical sensor fusion problem, but this is actually Different in the sense that you don't have to solve the calibration, you don't have to solve synchronization. It's totally from different sensor streams. You just have to do the map fusion. In this case, this really help is to really figure out how I can figure out the corresponding object in this. The quick design of this would be trying to find obvious objects aligned to each other. So in this case, planes in the physical space, we can detect them in the camera image reliably because they've been supported by many, many points. The accuracy will be pretty good. Also can detect them in the lidar readings, the point clouds, because again, similar story. Then we create an optimization-based approach to align them together. This actually not only can help rectify the visual SLAM result, also bring this into the word coordinate system. Because if you're familiar with the vision, you know that a camera is a bearing sensor. Does not give you proper size. But when we fuse this together, you will get a metric measurement. So with all this together, we run this map fusion algorithm, we can get a more reliable map. And more importantly, we can prove the covariance metrics of these landmarks in the combined map will be in each of these eigenvalue will be smaller than that of separate maps in the either lidar or camera alone. So that means accuracy is improved. And we also did that in the simulation by trying to adding more planes in this test case. You can see the robot is trying to move from start to end is a design trajectory in the indoor environment. We have 4 planes. When the plane was detected, if we're not using that, you can see uncertainty grows. This is very similar to the example I showed you earlier, because ellipsoid grow larger and large. But if we start adding the planes into this, the constraint help reduce the covariance and the uncertainty gets reduced. And of course, the map gets more accurate. All right, so of course we test that on the real environment in both the indoor data that collect in our own building, HRBB. We have this plans being used, many plans being used, and the trajectory be ratified is much better than pure visual SLAM or the lidar SLAM itself. Then we also run that in the open test data set, like typical Kitty data set in the city blocks, and do that. And we have the limit works better than any existing algorithm that provide at the time. We did a longer sequence of kilometer levels in length and still works. And this actually allow us to go into next. This is really the design for robustness to an extreme. So why we say this is we still want to solve localization problem in this example, but we really want to deal with the most extreme case situation. So what is the extreme case situation? Very bad weather, poor illumination conditions. You don't have any GPS signal. You don't have good visual features at all. You don't have even reliable lidar inputs. Even radar may get blocked with all the snows. And you still want to find your location, where you are in the city. So how do I do this? Because this is ultimate test for robustness. How do I do this? Well, we pick up the sensors that are not going to be affected. We design a map-based localization. We don't rely on any external perceptions in this case. Just trying to do a sensor fusion with a few sensors that are available to us, which means we will use IMUs on board of the vehicle. Limit the input from campus if we can obtain a stable reading. Of course, apply map. We're going to fuse this input to figure out where am I. The idea is relatively simple. If I can do a data reckoning with IMU and campus reading, I can extract a discrete set of the heading changes. So what you say is here we only use a minimal approach, only use the heading changes. Let's say this sequence, can I match this with the map? To create a map, find where am I? As long as the map is not like a Manhattan district that with everything's rectilinear, then I should have a chance to find where am I. But essentially, to do that, we also discretize the existing map in the heading representations. How heading changes is a discrete representation of the map. And this gives us an index data structure that we can quickly compare to our heading sequence that we extracted from the IMU and the campus readings. So this is basically give us really the minimum solution we need. I mean, this is work is done 3 years ago. Right now, we can also incorporate heading and the distance together to create a more reliable and more quick convergence on this. But for simplicity, we only use heading information here using the heading sequence. But what's important, we can prove mathematically that as the heading length increase, as long as they are not confined to the limit of set like a rectilinear environment, the Bayesian probability, conditional probability that you're going to find your true location will increase over time. And this is I encourage encouraging results that that probability really a function of how many intersections you have, how many potential headings you would have, and how many existing how complicated a map you have, and all this together give us the idea that if you're on a regular map, not the specialized rectilinear city, which actually interestingly we did find out about the literature talking about the city heading and the distributions over all the major cities in the U.S. and in the world. I found that the rectilinear environment is actually just a special case. Super majority of cities have a large distribution of headings, which really helped this algorithm to be successful. So we did test this on the Kitty dataset, in the Kitty, which is actually, the Kitty dataset is collected in Karlsruhe, Germany, and that city is pretty friendly to this particular approach. We also did that in our city college station, and to see how many observations, essentially how many turns I need to make to be able to find my location. On average, it takes about 6 to 8 turns before my algorithm be able to identify where am I in that map. It's not too bad. And in fact, in reality, if you get lost in such a bad environment, you can really drive your vehicle to help the algorithm to find where you are. And that will make the converge a lot faster. So that's kind of design for robustness idea behind it. And this gives you some of the examples on the trajectory that been driving until it finding its locations. So the next thing I want to do that is also the last part talk on the touch base that you can design new sensor using the sensor fusion idea. So this is actually an ongoing work that funded by National Science Foundation. So what we are dealing with in this, I completely get out the robot navigation domain here. I'm going to another traditional domain of robotics, and this is grasping. So we want to design a sensor, actually a sensor fusion type of sensor that can measure the object to be grasped, that actually the near distance ranging and the material type and the surface structure and whether it's a thin shell object or it's a solid object. This is why we need to do that. Because when the robot moving from the factory floor to more service market, it need to be able to deal with unknown object. Need to grasp unknown object. The objects that it does not store its shape, material type in its library. So, for example, human is very powerful. We can grab an egg or a dumbbell without breaking the egg, because we know what kind of material it's made of. We know the friction coefficient. Empirically, of course, we can get the idea how much force we should apply, how we can grasp it. I guess there is a question pop up and say, have you done any research on pure alternative vehicle direction? Of course, not yet. Well, not that topic I'm presenting right now. It's not at this moment. They are talking about grasping. So basically, the robot needs to be able to know the material type in the structure, internal structure of the object to have a reliable grasping. So common approach would be you want to use a camera light to recognize this, but problem is when you're getting close to the object to be grasped, occlusion will block you to get a precise pose estimation. And also appearance can be deceiving. So, with the same pen pattern, you don't know the material type underneath it. Or you might use tactile sensing like human grasping. Problem is any tactile sensor require you to contact the object. The contact itself may either damage the object or change the configuration of the object to make your grasping plan fail. Or you might use a proximity sensor, but existing proximity sensors have problems of dealing with general objects. And this is kind of a challenge. So that's why grasping also be considered a grand challenge of robotics, reliable grasping. Now, our belief is maybe we can design a new sensor to help it. So what is this new sensor gonna do? It's built under something called optoacoustic effect. So what does that mean? We're shooting short laser beams to the object. When the laser beam, the excited object, they will create a vibration and ultrasonic vibration and return ultrasonic signal. This is called optoacoustic effect. You can immediately think this is actually using two modalities at the same time already. And we can receive both we receive the acoustic signals. We can perform spectrum analysis because that mechanical vibration carry both the material type information and what kind of structure it underneath it. And this kind of idea of design this sensor, basically we want to put this in the robot finger. The walking distance of this sensor usually about like less than 1 centimeter away from the object. Before you contact object, the laser beam is fired, and I can know what kind of object, what type of material this object composed of. Is this a thin shell, porous, or solid material type? Then it can help me with grasping. So a prototype is being built, and we are testing it at this moment. You can see this is basically doing sensor fusion at the really front end of the data flow, where you acquire the data, in fact. So we test on different materials, steel, acrylic, and rubber, and we actually trying to build a set of the library for other possible materials. So we are in the process of doing this, doing material scanning. We also we are, in fact, have a fingertip slam. So we are doing the reconstruction material on the fly into shape and type of material distribution before the grasping is actually, so can help with the robot grasper come up with better plans for by this, the data to improve the successful rate of the grasping, to increase that. So that's kind of the idea of during the new sensor design with the sensor fusion in mind. This is really to move the sensor fusion to the front end. So that's actually quickly summarized my talk. There are other things going on. In my lab, we're still doing autonomous vehicle research. We're actually leading a team to compete with Auto Drive Challenge that organized by General Motors. We're currently the best team in the US, the second best in the world. We also have, working with American Railway Association, develop inspection algorithm for railway buckling. This also a sensor fusion approach. Also my group was pretty active in the animal detection, the natural environment observation applications, and also storm tracking with UAV and things like that. If due to time, I'm not going to go into these projects, but feel free to visit our webpage to learn more about it. That pretty much concludes my talk. Any questions?
If you do have any questions, feel free to write them into the little Q&A box. The first one, we already have one, was, have you done any research on purely autonomous vehicle direction?
Yeah, of course, we do. I do have a wide range of research projects, not just the autonomous vehicle. It's from grasping to indoor robots, to small robots to bigger robots, and also UAVs. The whole we do have different projects. Yeah.
In data fusion, do you fuse raw data, or do you need to extract some features from the raw data, then fuse the features?
We do all of them. That's a quick answer. We even think about, from the talk, you can see that we even think about how to get those raw data to, yeah, we do have, for the correspondence problem, we did a feature-based, we apply essentially as a feature. We also have, raw data-based fusion. And if you do some of them, I didn't present here, we did some CNN-based approach too. That's pure data-driven approach. But personally, I'm still kind of a guy who like a model-based approach. So most of them are model-based from my research area. Yeah.
Is computational load also an aspect considered for the sensor fusion process?
Indeed. So that's the one shortcoming of sensor fusion. You have to compute them all. So we do also have works in this domain trying to speed up, whether using parallel computation or we design new optimization engines to use the sparse nature of the data to accelerate optimization. In fact, my student and I, we work on how to improve the speed of this thing called G2O, the common optimization, sparse optimization framework used in the SLAM. And that's a lot of things can be done there. You can also use hardware acceleration if you really need it. All the autonomous vehicle we are developing have to use some sort of hardware acceleration to tackle the large amount of sensor data.
All right, any other questions? We do have one, hold on. Do sensors have to be redundant for fusing? If no overlap, is it hard to perform fusing?
That's a very good question. So we do have the example here in the early talk. Is that GPR camera fusion problems. There's no overlap between the perspectives. But in some cases, they do have overlap in, for example, in the autonomous driving scenarios, many of them have overlap. LiDAR and camera have a very large overlaps. The difficulty definitely exists if you don't have if you have a non-overlap situation. The difficulty really is calibration. Computing the spatial transformation between non-overlap sensors require additional device help. For overlapping situations, more standard, I would say. Yeah.
Are there any cognition-based approaches for sensor fusion?
I believe so. I've seen some, but this is not the main approach of my lab. Some of my collaborators using different cognitive models to do that. But it's going to be, it is really, I think, the application dependent in that approach. So I'm not an expert on that approach. So I would say they exist, but it could probably worth looking into. Yeah.
Great. Okay, that actually takes us to the end of the hour. So I want to thank our speaker and thank all our attendees for coming. And I hope everyone has a great day and a wonderful weekend.
Thank you.